Hello, I'd like to cover the questions that were asked in office hours for Unit 5, Module 3A homework and for the pop quiz that is happening today. Right, so we're going to go through several questions that you will be asked on the homework and pop quiz. So the first thing is that we're talking about mechanisms. And mechanisms are going to be given in what are called elementary steps. And they'll be numbered like step 1, step 2, in a reaction. And you're going to be asked to identify their roles and how they sum up to the overall reaction. Right, so when we look at this particular mechanism, what we see is in step 1, we have NO2 breaking up into NO plus O. O plus O2, once O is made, it reacts with O2 to make O3. When we sum up the overall reaction, we just take all the reactants from all the steps, sum them up, and put them on one side. Then we sum up all the products from the two steps on the other side. We cancel any term that's on both sides, and that gives us, as an overall reaction, NO2 plus O2 making NO plus O3. So this helps us identify the roles. We have reaction 1 plus reaction 2 making product 1 and product 2. And that also helps us identify that O is an intermediate whose characteristics are they start as a product, meaning they're made usually in step 1, and then are a reactant in step 2. When you do the overall reaction, they're not present because they usually cancel on both sides. So we would agree that NO2 is a reactant, but O is not a product. O2 is a reactant, and O3 is a product. We'd agree with that. O is an intermediate, yes, but NO is a reactant. Nope, it is a product. Okay, so this is what you'd want to make sure that when you see a reaction, you know the roles of each of the substances, and you know the overall reaction. Okay, so in this case we have a single step mechanism, we're told that. And since we have a single step mechanism, we can consider it an elementary step. And if it's an elementary, so all elementary steps you can write the rate law as a function of the concentration and powers. The powers are the coefficients, just like we saw with equilibrium constants, except in this case we're only considering the reactants, right? The reactants. So we have the same rules, but they are only for reactants. So single step means elementary step. So we can write the rate. So the coefficients here are 1. So the rate is going to be K. K is our proportionality constant, our rate constant. We will explore that more next week. And so when so Cl to the first power, O2 to the first power. Those coefficients come from the stoichiometric values. And that gives us answer B. Same rules for equilibrium as we have for equilibrium constants. Must be aqueous or a gas. So that's supposed to be aqueous there. Aqueous or a gas, right? No solids or liquids, pure liquids. Must be aqueous or gas. Okay, here in this problem, you're given the rate law, right? So we're given an overall reaction, and we're given the rate law. And just keep in mind, if you're given an overall reaction, this cannot be used to determine the rate law. Just because you have the overall reaction, you need elementary steps. Here we don't have elementary steps, but we're given the rate law. And so now the question is, how many times faster if we change the concentrations? Okay, so this is built by taking the ratio of the new rate, right, with the new concentrations, over the old rate, and this gives you either what's called the factor or how many times faster. So you'll see this, by what factor does the reaction, is it faster or how many times faster? You'll see this a lot. So what we do is we just put in the rate law, and then we just write the changes that have been made, right? So we're doubling how much A there is, and we raise that to the third power. We're tripling the amount of B, and we raise that to the 0 power. And now we're just dividing it by the rate law of just how much if we had A and if we had B. And the advantage of doing that is what we see is a bunch of terms are going to cancel now. So if we we distribute the exponents here just to make it easier to see. So it looks like that. That's our numerator. And the denominator, we still have K, we have A cubed and B cubed, or B to 0. And so now a bunch of terms cancel. And we're just left with the coefficients. And so now the value is 8. So anytime you're asked to do how many times faster is a reaction, kind of use this formulism. You just take rate new over rate old and just put the what's changed and just sort of treat it all in parentheses. And then you have your exponents, and this will be an easy way to track the answer and to generate responses if it's a free response question. Right. So here we have a multi-step, elementary step here, reaction, 3 steps. And here we're given the rate law. We're going to be talking about how to find the rate law in the next couple slides. But in this case, we're given the rate law and want to know what's true. So this is a semi-quantitative problem. So we're given the rate law. So we're just going to use the same ratios here. We see it second order. So the rate new over rate old is K. So we're doubling how much of CLO there is. So we double how much there is, but we keep it inside the parenthesis. We square it because it's second order. And the old would have just been if it wasn't doubled. When we do that, we see that we can simplify this way and then cancel out these terms, and now we see it quadruples. Okay, so it quadruples. That's the second order result. If it only doubled, which is answer A, that would have been first order. If it had not changed at all, it would have been 0 order, right? But we know that it was given second order. And then if it was cut in half, the only way that could happen is if the concentration was in the denominator, and that was not true. The concentration was in the numerator of the rate law. All right, so now we're going to get into several examples of how we assign rate laws, knowing something about the fast-slow steps. Right, so let's take a look at first the data given. So we're told that the rate law is first order in SO2 because it has a linear relationship of the rate law of the rate versus concentration. And so what we're going to do is we're going to write as we talked about in class, the rate of a reaction is uniquely determined by the slowest step. So the slowest step will always determine the rate law. So what we're going to do is just write the rate law from the slowest step. So for mechanism 2, the slowest step is NO times O2. And remember, we raise it to the 1/2 power because of the 1/2 coefficient. Okay, so there's no SO2 in this rate law in mechanism 2. There's no SO2 in the slow step, so we know right away that this has to be a 0 order SO2, right? So if we were to rewrite it, it would look like this, SO2 to the 0 power, and that's because it's not present. So SO2 is a 0 order, and it cannot have the behavior in the graph given. Okay, but now let's look at mechanism 1. So mechanism 1, when we write the rate law of the slow step, we get K times NO2 times SO2. So here we have SO2 appearing in the rate law as a first order reactant. All right, so that's exactly what we're looking for. This is first order. It should be linear, rate versus SO2. As long as we keep NO2 or whatever other term that's going to be there constant, SO2 will have this relationship. So this rate versus concentration is consistent with mechanism 1. Okay, so the rate versus concentration of SO2, this is independent, zero order. That would be mechanism 2. So mechanism 2 would be flat, while mechanism 1 would be linear with SO2. Now it turns out that although this rate law, this slow rate law, was perfectly fine for determining whether it was first order in SO2 or not, it is not a valid overall rate law, and we're going to talk about how we can generate valid overall rate laws from the fast-slow mechanism. Okay, so we're going to do that now. Okay, so how do we generate, so we're going to do, so we'll do this. So how do we generate the rate law? So we generate the rate law by first, rate is first determined by, it's going to be a 3-step process. Step 1 is always construct the rate law from the slowest elementary step, right? That is the most important thing we do. So that means the rate is just NO2, just like we had it before, times SO2. Now, what's the issue? The issue is when we look at the roles of NO2 and SO2, SO2 is fine, it's a reactant, but NO2 is an intermediate. It is not in the overall reaction. It's made first, then consumed in step 2. It's an intermediate. And so we can put all the roles here. So first we have a catalyst, NO. It starts as a reactant, and then it ends as a product. It's also not in the overall reaction. So what we have to do now is in step 2, we have to find an expression to substitute for the intermediate, and we do that from writing Kc from step 1. So Kc is the products over the reactants. So we have NO2 divided by NO times O2 to the 1/2. That's how we would construct Kc. And so now, in the final step, we can solve for the concentration of the intermediate, and we're going to substitute into step 1. So we do that for NO2, we get Kc is equal to NO times O2 to the 1/2. And so if we substitute that expression into step 1, we get, we're substituting in for concentration of NO2, and we get this expression. So K times Kc, NO, NO2 to the 1/2. That's what NO2 was. And then times SO2, which was already present. We're going to combine the constants, the rate constant and the equilibrium constant, into some new constant. Don't really care about it, but we just call it K prime. And then we have NO to the first power, O2 to the 1/2, and SO2. All right, so that would be our overall rate law. So let's try to summarize this. Catalysts, which is NO, can be in the rate law. You can add catalysts, you can control catalysts. Catalysts can be in the rate law. Catalysts start as reactants and end as products. Intermediates cannot be in the rate law. They start as products and they end as reactants, and that's why you can't use it in a rate law, because they start as products. You cannot directly control the concentration of the intermediate. All right, so this question came up in office hours, so let's take a look at it. Well, we have two different mechanisms here. We're given some information about the overall reaction, and we want to match it to an energy diagram. All right, so let's take a look. So first of all, anytime you see the slow step, slow means high activation energy. right? It takes more energy to get over the barrier, and so that step happens slower. And then we have fast steps, which means low activation energy. That means it happens faster because there's a smaller barrier that the particles have to overcome to react. So let's just take a look at options A, B, and C from the standpoint of step 1 and step 2 from the activation energies. So when we look at that, this is relative within an energy diagram. So step 1 and 2 for A is high-low. And what does that mean? That means the first step is slow, the second step is fast. We could do that for all four graphs. Step 1 in B is low activation energy, high activation energy. In C, it's high activation energy, then low activation energy. And then in D, it's fast, low activation energy, then high, slow. All right, so that helps us assign the relative speeds of the steps. And what we see here is that each one of these are consistent with the mechanism, right? So slow, fast is consistent with step 1, mechanism 1, and fast, slow is consistent with mechanism 2. Now what we're going to do is just take a look at, is it endothermic, exothermic in step 1 and 2, and in the overall reaction. So for option A, it's exo-exo. Option B, it's also exo-exo. C is endo-endo, and D is endo-endo. And then the overall is exothermic here for A and B, and for C and D, it's overall endothermic. Okay, so that helps us identify sort of what are these energy diagrams telling us, and what do we need to connect to the mechanism to pick the right answer. Okay, so first we look at the overall reaction. So the overall reaction was given to us. Delta H is negative. Delta H is negative, it's exothermic. So that's given. We can look at step 1. Step 1 is really the only step that is clearly assignable. Step 1 is 2 reactants making 1 product. We know this is exothermic. 2 particles making 1 particle, net bond formation, exothermic. Step 2, 2 particles making 2 particles, AB bonds on both sides. Questions, not really sure. Probably won't be used definitively. So now what we could do is, well, we can first of all exclude C and D, because overall reaction is not endothermic, so we're really only dealing with A and B, the ones that designate exothermic behavior for A and B. And then now we're looking at step 1, right? So step 1, So in mechanism in A, we are going slow, fast, and it's exo. And so we would assign Roman numeral 1 to letter A because it has the right exothermic and it's slow, fast. We would assign Roman numeral 2 to energy diagram B because it has the fast, slow, exothermic, and exothermic. So that's how we would use this information to pick the 2 energy diagrams, one for Roman numeral 1 and one for Roman numeral 2. Okay, so another fast-slow mechanism. So we will kind of go through this a little bit in a more brief way than we have. So we'll do the 3 steps. Step 1 is writing the rate law for the slow step, K times D times A. The roles are intermediate times reactant. So that means we have to substitute for the intermediate by writing out Kc. And here are the roles. And so Kc here is going to be C times D. Those are the products of step 1 times A times B, the reactants of step 1. We can now solve for D in terms of Kc, A, B, and C. And now we're going to substitute. So we want to substitute out for D, for the intermediate. So we get the rate law, which was A times D. That was our slow step, but now we want to substitute for it. And we put in everything that concentration of D equals. And we kind of combine terms. And we get A squared times B divided by C. And remember, we're just going to combine K times Kc and just turn it into one constant, right? One constant. So our final rate law is A squared times B divided by C. That would be option letter D. So the more you practice the fast-slow mechanism, the more you'll see it's always 3 steps, and it's done this way. All right, so I just wanted to do this one over again because we get a lot of questions about it in office hours, and I just want to show it a little bit clearer. So fast-slow, slow step, again, intermediate times reactant. We write Kc from step 1, where the intermediate was generated. We solve for it by putting Kc and the other reactants together. We can now substitute, right? So here's the portion of the rate, the slow step, that's perfectly fine, K times SO2, but now we have to substitute out for NO2. We can include the catalyst, NO. We make the substitution, and this becomes our rate law, which is option A. Okay, so option A. So it's a really good thing to practice. So we had more than a couple questions in office hours about problems like this. So let's talk about first the fast-slow. So this reaction is fast-slow. Why? Because the activation energy is low, then high. And now we want to write out the individual reaction steps. So what we see is A2 plus B making A2B. And then in step 2, that's the intermediate. The intermediate then reacts with B again to make A2B. Okay? So what students often mistake is, where do I put this B that's right there in the middle? And so you can kind of think of this as just a reactant waiting for the intermediate to form, and then once the intermediate forms, it reacts with it. So we put an arrow there. So you definitely don't want to put it in step as a product of step 1, because that'll mess up the stoichiometry. So we're really saying it's just that once A2B is made, then it reacts in step 2 to make the final product. Okay, so this is fast, slow. So we have our A2B, that's our, so our rate here for the slow step is A2B times B, but because A2B is intermediate, we have to write the equilibrium constant to form an expression for it, which we do. It is Kc A times B. Now we can make the substitution for A. It's actually A2. I'll make that correction now. So A2 times B, there we go. And now the rate can be written as K prime A2 times B squared, right? So times B squared. So we have quadratic in B, linear in A2, and that's how we would analyze this problem. First, from the fast slope, we need to get the information from the energy diagram and then write out the individual steps. Okay, so I'd just like to summarize here. Number 1, elementary steps are used to determine the overall rate law. So that's what you want to make sure is clear. You never get it from the overall reaction unless you're told it's a single step reaction, right? So slowest step determines the rate law. That is the highest activation energy step. 2, a single step is an elementary step, right? It's the only step, it's the elementary step. You can use it to write the rate law. Slow, fast, the most straightforward mechanism, which is the rate law is always constructed from the first step. Fast, slow is a 3-step process. You have to write the rate law of the slow step. 2, write Kc from step 1. and 3, substitute for the intermediate, right? So those are the 3 steps. We did several examples in this video. Really encourage you to practice those and make sure you have them available on your page of notes. And here's how we would graph the different responses of concentrations versus reactants. So let's take a look at this. First, zero order, right? So if you have a reactant that is not in the rate law, that is going to be zero order. If you have a rate law that is proportional to the first power of a reactant, then it will be first order kinetics. Second order, which is quadratic, would be that it's proportional to the square, and it would be quadratic. But it must have an exponent of 2 to have this shape. All right, so with that, good luck. If you have any questions, please stay for office hours. Post on Discord. This should help you. I really encourage you to use it or look at it before you take the quiz or after you take the quiz to evaluate your answers, or use it to do the homework.